Today's NIA webinar. Where does your kit fit in a nuclear safety case? We are pleased to be joined by Stephen Kidd. Welcome, Stephen, who is the civil safety case lead at Corporate Risk Associates and also head of discipline for safety at Assystem Limited. Stephen is going to present the evolution of the nuclear safety case in the UK and help us understand how a piece of kit, cog, service, etc., fits into a safety case for a nuclear facility to demonstrate the risk of operations is as low as reasonably practicable, ALARP. Stephen's going to present for around 40 minutes. Then there'll be a Q&A session. You can submit any questions at any time during the session through your Q&A function. You can submit questions anonymously if you prefer, and these will be addressed at the end of the Q&A session at the end. The slides and a recording of today's presentation will be available in the members area of the NIA website later this week. I'll now briefly introduce Stephen. He's got 20 years experience providing safety and assurance services to the UK civil and defence nuclear sectors. He's worked both in consultancy and within a UK licensee, with experience of nuclear projects at all stages in the life cycle, from initial hazard identification through to decommissioning. For the last decade, Stephen has worked on various UK projects, the UK AGR fleet and UK new build projects, for example, Hitachi GE in their GDA submission, Horizon Nuclear Power and NMB Genco for Wilver-Newith and the HPC projects respectively. So welcome, Stephen. Thank you.
Thank you, Gareth. And thank you to the NIA for this opportunity to speak to you all today. Good afternoon, everybody. Can you see my screen? Oh, not yet.
Not yet.
There we go.
Perfect.
Okay. So what the session will cover, Gareth has given a summary there, but just generally what I'm going to try and cover at a very high level today is a bit of an introduction to myself and CRA. I'll skip quickly through that. A bit of a background to nuclear safety and nuclear safety cases. I'll also give a high level overview of safety cases and safety case principles, and then what does that mean for plant and equipment. And there'll be an opportunity to ask questions at the end, but as Gareth said, if you want to ask any during, you can use the Q&A function to do that. So, sorry, I just need to get this on the right screen. So yeah, I think Gareth's covered most of this stuff about me, so I'll just skip quickly over that. As he said, I work for CRA, I'm Chief Consultant and Civil Safety Case Lead. I'm originally from an electrical and mechanical background, but I've got an MSc in nuclear science and technology. And I've worked both with in licensees and within consultancy in the UK nuclear industry for around 20 years. In my current role, I'm responsible for capability development in the safety case area for CRA and Assystem, business development and managing client relationships. And then if I've got any time left over, I still like to get involved in some technical delivery as well. So briefly, just a summary of CRA. I joined CRA about 18 months ago, and prior to that, I wasn't particularly familiar with them myself. I saw them as predominantly a probabilistic safety assessment company, which was their core business. It was set up about 20 years ago, mainly to deliver PSA services and risk assessment. That's evolved over the last few years to expand out into safety case. So we've got safety case capability. Also human factors. They've got an expanding human factors team and strong human factors capability, and nuclear and civil structural and engineering substantiation, as well as some research and advanced risk analytics work. So quite a broad capability now, and covers most of the safety case life cycle. And I'd get in trouble if I didn't mention this as well. CRA, we host an annual risk seminar, risk forum. Basically, there's speakers from around the UK nuclear industry and other high hazard industries, and also from around Europe and worldwide. It's generally held around September time. Last year was a virtual session, which was quite successful, well, for obvious reasons. We're not sure whether this year will be virtual again. I suspect probably will be, but if you keep an eye out for that, it's always a good event. So getting on to the main topic, why are we obsessed with nuclear safety? Well, you're probably familiar with these events. Well, certainly the latter ones anyway. In the nuclear industry, things don't go wrong very often. We've got a good safety track record, a good history of operating safely, but when they do go wrong, they do tend to go wrong in quite a big way. So these events here were quite significant, and they influence the public perception of nuclear as an industry, and it's very hard to come back from that. So we need to be able to demonstrate that we're learning from these types of events and doing everything we can to make the industry safe. So how do we go about doing that? Well, we need to understand the risks associated with the operations and plant and materials that we're using. So to do that, we need to understand what can go wrong, and then how likely that is to go wrong. So what are the faults or hazards that we need to worry about, and how credible are they to occur? And if they do occur, then what are the consequences? Is it just localized contamination or a small dose to some operators, or there's a potential for significant off-site release? We then need to have a think about what things we can put in place to stop those events happening. And then we need to ultimately assess whether those measures that we do put in place are good enough. Are we satisfied that they are adequately mitigating the risk? So to help us to do that, there's legislation and there's our nuclear regulatory framework in the UK. I'm not going to dwell too long on legislation. It's not particularly exciting. I've got some links at the end of the presentation if people are interested in going to find out a bit more themselves, but I'll try and touch on some of the more relevant pieces of legislation that underpin nuclear safety cases in the UK. So I've highlighted there that there's legislation supported by codes of practice, and there's the regulatory framework. I will talk about it more in a minute, but the Office for Nuclear Regulation, the UK regulator, has got a lot of useful information on their website as well, and I've provided a link there to that. So this may seem a bit strange. We're talking about nuclear safety cases, and now I'm talking about a national coal board court case from the 1940s. But this is really where the origins of reasonable practicability, or reasonably practicable came about, which is what underpins everything we do in nuclear safety cases. So there was an accident, and Mr. Edwards died when a mine roadway collapsed. And in their defense, the National Coal Board said that it wasn't practicable for them it was too expensive to shore up every roadway. And therefore, they couldn't have prevented the accident occurring. So in summing up, the judge made this statement. I won't read it all out to you, but it basically defined the term reasonably practicable. So it's not what's physically possible, it's narrower than that. You can take account of the time, trouble, and effort involved in mitigating or preventing the risk. And if that is in great disproportion, then you don't have to implement further risk reduction measures. So that this basically is the basis of the UK health and safety legislation on the nuclear safety case framework. So this term ALARP, I'm sure a lot of you are familiar with it. It's basically how the definition of reasonably practicable arises from the Health and Safety at Work Act 1974, which is a piece of legislation that It's an enabling act. It allows other legislation to be placed underneath it. And it outlines the duty of care of businesses, organizations to their employees, and to protect them from the risks associated with their work environment. The whole idea of ALARP, the risk must be significant in relation to the sacrifice in terms of time, trouble, or cost. So if the level of risk reduction you're gaining is very small, but the cost and time or money is very high, then you can justify not doing it. But equally, you have to be able to demonstrate that gross disproportion to justify not doing things. So it's weighted in favor of carrying out safety improvements. It's not a simple cost benefit where you're just weighing money against the potential benefit. If the result comes out that it's not massively disproportionate, then you're still expected to implement those safety measures. And ultimately, all safety cases must demonstrate that the residual risks remaining are ALARP. So once you put all your safety measures in place, you need to be able to confidently say that the risk has been reduced as far as it's reasonably practicable to do so. So here's some other bits of key legislation. There's the Nuclear Installations Act 1965. This makes provisions for licensing. So all sites and operations that involve significant quantities of nuclear material, such as reactor sites or rad waste processing sites, things like that, will require a nuclear site license to operate. And that's granted by the regulatory body. There's the Energy Act 2013 that established the Office for Nuclear Regulation, which is our regulator in the UK. It was previously the Nuclear Installations Inspectorate before that. And that Energy Act gave them their powers to undertake enforcement action and regulate licensees in the UK and nuclear sites in the UK. And another important piece of legislation is the ionizing radiations regulations, which define the exposure limits in the UK. So these are legal limits that companies who handle and process nuclear material are obliged to ensure that they remain within, and that their employees are not in breach of these limits. So I mentioned a site license. So a site license is granted to the operator of the site. It includes 36 standard conditions. There's some of them summarized here that are more relevant to the safety case and plant items, which is what we're talking about today. So the key one as far as the safety case is concerned is number 14 there, safety documentation. That's basically what outlines the requirement to have a safety case. 15, periodic review requires operators, once they've established the safety case, to regularly review it and maintain it and ensure that it remains aligned with the actual condition of the plant. Conditions 19, 20, and 22 cover modifications to the plant at different stages in the life cycle. So during design or construction or actual during operation. 23 and 24 are associated with procedural, so operating rules and instructions, so procedural controls. And 27 and 28, they're associated with the sort of things I'm going to talk about later in this presentation. They're the safety measures, so the engineered equipment we put in place to protect, prevent, and mitigate, and the examination, inspection, and maintenance and testing arrangements that support those. So there's a link there at the bottom as well to the License Condition Handbook, which is the ONR's handbook with all 36 license conditions and the expectations outlined underneath each of them. So I've mentioned safety case quite a lot already. Safety case principles. So the ONR have what's called the safety assessment principles. Now, they're quite clear that these are for their inspectors to undertake their assessment. They're not for licensees to demonstrate compliance against. But obviously, it would be remiss of a licensee to not take account of what the regulator's expectations are. They cover deterministic and probabilistic principles. We'll get onto that in a minute. and they're supported by a set of technical assessment guides which help the O&R assessors to undertake their assessment and set expectations against each of the license conditions. So individual licensees, like I said, they're not expected to demonstrate compliance against the O&R SAPs, but they are required to have in place their own safety management arrangements to satisfy themselves that they are effectively controlling the risk of their operations on their site. And this, more often than not, involves developing their own equivalent set of safety principles, which might map quite closely across some of the SAPs and also IEA guidance. So what is a safety case then? I'm not going to get into great detail here, but I'll try and give a very high level summary of some of the main concepts and main aspects of a nuclear safety case. So this is the regulator's definition. A safety case is a logical and hierarchical set of documents that describe risks in terms of hazards presented by the facility, the site, and the modes of operation, including potential faults and accidents. So it's basically the totality of the documentation. It tends not to be a single document. It's a full suite of documents that include the safety case presented in safety arguments, supporting analysis, substantiation, qualification, evidence that underpins the arguments and claims made in the top level safety documentation. So it encompasses quite a lot of documents and evidence. It's not just a single document. I mean, people talk about the safety case, but it tends to be a large set of documentation. And ultimately, the aim of it is just to demonstrate that risks have been adequately managed and are ALARP. The purpose of it is not to demonstrate that to the regulator. It's ultimately for the licensee to satisfy themselves that they've done everything they need to adequately manage the risks associated with their facilities and operations. And I like to think of it about it being the story. So it explains what the risks are, how they're being managed and mitigated, and then justifies why that ultimately is adequate and ALARP. So this is another key concept of the safety case. It's defense in depth. So this is introduced by the International Atomic Energy Authority. There's a link at the back to one of their INSAG documents that talks about this in detail. But basically, it's about implementing measures at different stages to try and control risk and prevent or prevent accidents and mitigate the consequences. So level one is really to do with design. So we design things robustly. We design out problems and potential faults and hazards. Level two is about controlling sort of abnormal or deviations from normal operations. So it's about detecting potential failures and making sure that those don't escalate into actual fault scenarios or accident scenarios. And level three tends to be where most of the safety measures and things that we talk about or are going to talk about exist. This is where we've got faults occurring and we've got specified safety measures in place that are designed to protect against them escalating to the point where they become an accident and there's a significant release. Level four is about severe accidents. So these are some scenarios to account for if particular severe challenges. It might be extended loss of off-site power, for instance, combined with common cause failure of diesel generators and things. These are extreme scenarios that are looked at, and also to account for potential errors in the analysis supporting the level three measures. And then ultimately level five is looking at, well, mitigating the off-site consequences. We've had an accident and how do we deal with it, emergency planning and emergency arrangements and things. So it's all based around prevention, protection and mitigation ultimately. So I've mentioned deterministic and probabilistic assessment already. It's not an either or thing. We use both in safety cases. So what's the difference? Well, deterministic is a qualitative assessment. We undertaken against an identified design basis. So we identify our design basis, faults and hazards and challenges, and we provide robust engineered solutions to ensure that the plant is capable of dealing with those events. There are, I say it's qualitative, but there can be quantitative aspects to it as well. Excuse me. Probabilistic is more focused on quantitative, as it suggests. It's a numerical assessment of risk, and it's particularly useful for assessing the risk of the ongoing risk of through plant operational life. You can look at things like maintenance. If we're taking plant out for maintenance, what impact that has on the risk, or we can look at modifications and the impact of those on the overall risk. And it allows a sort of assessment of potential options as well when we're looking at modifications. So they're complementary techniques. Together, they build up a risk profile of the plant and help to demonstrate that the risk is ultimately ALARP. I mean, I've talked a lot about risk. Should possibly define that a bit earlier, but it's generally a combination of the frequency and the consequences of an unwanted event. Initiating events is another term we come across quite a lot, which is the initial event in a fault sequence. So it could be a hazard, or it could be a plant fault or a human error that kicks off the chain of events that, if unmitigated, if there's nothing put in place to stop them, could result in release of radioactivity. And safety functions is another useful term. So when we're looking at the plant, we identify safety functions, things that the plant and processes need to deliver to ensure that nuclear safety is maintained. And systems, structure systems and components, these are effectively the safety measures that we put in place, the engineered systems that are there to deliver the safety functions and ensure that nuclear safety is maintained. So expanding on the safety function idea a little bit more, if we're talking about reactor plant, which we'll focus on here, obviously there's other types of nuclear processing plant things that would have slightly different basic safety functions. But from the perspective of a reactor, there are three main safety functions, three main things we need to do. We need to control the nuclear reaction. We need to control the activity. So we need to be able to shut the plant down safely in the event that a fault occurs and maintain it shut down. We also need to remove heat from the core, both during normal operation and during fault sequences, and also all the way through the fuel route as well. Once the fuel's out of the core, we still need to cool it and make sure that there's adequate cooling. And confinement. So at all stages, we need to make sure that we're containing and confining radioactive material and providing sufficient shielding to our operators and barriers against the release to the environment. So these are basically the fundamental functions of safety functions for a reactor plant: control, cool, and confine. We then generally take these safety functions and we'll break them down further into specific safety functional requirements. So to deliver these these top level safety functions, we'll identify functions on specific systems or specific plant, or it could be humans as well, that things that they need to do that will contribute to the delivery of these top level safety functions. And if we can satisfy ourselves with delivering these three top level safety functions, then we're probably going to be ALARP. So this is just a quick slide to give an example of the sorts of things that we could be SSCs. It could be, you could be supplying pipework and valves for the primary circuit. It could be pumps that are being used to provide post-trip cooling. It could be instrumentation and control from the sort of post-trip sequencing and control systems, all the way down to it might just be individual sensors that are used in some part of the plant or possibly within the reactor itself, or electrical cabling or equipment and switchgear. So it covers the full range of things from huge plant items. You might supply turbines, or it might just be single valves. But all of these things can have specific claims that are derived from the safety case, and specific requirements that they need to demonstrate. So the safety case itself, you may well have heard this claims, arguments, evidence before. It's basically a legal argument approach where you make a claim, you support it with arguments, and then that ultimately is supported by evidence. So it's the same in safety cases, whether that's explicit, where the safety case is structured with clearly stated claims, arguments, and evidence, or implicit, you are ultimately making claims that need to be substantiated with evidence. So a claim is an assertion. It might be something like, my plant is safe to operate. So what sort of arguments would you need to support that? It could be things like, we've got suitable and sufficient safety measures in place to ensure that it's adequately safe. And that in itself doesn't just justify that it's safe to operate. So we need to provide the evidence to underpin that. So that will include everything from the hazard identification, that is defining what the hazards and the faults are that are of concern, to the fault analysis that's deriving the safety measures that need to be put in place and the requirements on those, with the risk model as well, where we can demonstrate what the residual risk is, and then down to substantiation and qualification of the structure, systems, and components themselves, demonstrating that they are functionally capable of delivering the requirements that they need to in all of the conditions, fault conditions and normal operations and things that they need to. So if we just quickly going back to ALARP, there's really two key requirements. We've talked about gross disproportion already. That's where the time, trouble, and cost needs to be shown to be grossly disproportionate. But there's another aspect to it as well. As a minimum, we need to demonstrate relevant good practice, and that could be application of specific design codes or company procedures or particular types of analysis. It's effectively what's seen within the industry as the minimum sort of acceptable good practice. So this, you may have seen this diagram before. It's referred to as a carrot diagram, and all that really does is identify these three separate regions where showing what depending on what the risk to the workers and public is, what we need to be doing. So the intolerable region at the top is well, as it says, it's intolerable. We can't be in there. The risk's too high, and we need to do something about it to move down. In the middle region, it's tolerable if ALARP. That means that we can accept being in that region as long as we are confident that we have implemented all reasonably practicable safety measures and that we are applying relevant good practice. And if the risk is sufficiently low, there's this broadly acceptable region. But even within that itself, we still have to demonstrate relevant good practice, albeit that the level of time and effort we need to put into it might not be that significant, but we still have to satisfy ourselves that we're applying relevant good practice as a minimum. And the importance of that will come out in a minute. So a high-level safety case process. I mean, this is very, very high level, but if we go back to some of the questions that posed at the start about what can go wrong and how do we stop it. So that's where the hazard identification comes in. That's where we do a systematic look at what can go wrong, what are the potential hazards and plant failures and operator errors that can happen that can cause unwanted events. And that includes identifying candidate safety measures. So what type of things could we do to prevent those faults or hazards from occurring or mitigate the consequences of them. And it's an iterative process. At this stage, it should be informing the design, so we might be able to design things out. But ultimately, we'll identify a set of faults that associate with the plant or process that we need to to assess further, and we need to identify appropriate safety measures for. So this goes into the fault assessment, and so we undertake our deterministic and probabilistic assessments. We'll develop our fault schedule, confirm what the SSCs are, and derive the safety functional requirements on those SSCs. And then ultimately we need to demonstrate, well, is what we've implemented good enough? And that's through the demonstrating the functional capability of the SSCs, that they can deliver the safety functional requirements on them, supported by key evidence provided by the equipment qualification. So there's another process that helps us, categorization and classification. So it's licensee specific. Again, there's IAEA guidance there. There's a link to that at the end of the presentation as well. But this basically enables us to identify the requirements on SSCs based on the contribution they're making to nuclear safety. So it gives us a framework to identify what we need to do to satisfy ourselves that the systems we're putting in place are adequate and suitably robust. So we've got a systematic hazard identification talked about that identifies the safety functions. So the safety functions are categorized. They're categorized A, B, and C on the basis of the potential consequences associated with failing to meet them. And beneath the safety functions, the safety measures, the SSCs that we put in place to deliver them, they're classified on the basis of their contribution to delivery of those safety functions. So if it's a Class A safety function, that's the highest level safety function. Sorry, it's a Category A safety function, the highest level safety function, and a Class 1, then it would be a Class 1 SSC that was the principal means of delivering that. For example, the reactor trip systems, the control rod systems are generally Class 1. If you had a secondary shutdown system, that would probably be Class 2. And the other benefit of having categorization and classification framework is it helps us identify the non-functional requirements. So it might be quality arrangements, quality requirements we need to demonstrate, applicable standards and design margins. So depending on the class of equipment, we might want to design it against more onerous challenges to give ourselves improved confidence in its ability to do what it needs to do. And there might also be specific integrity or architecture requirements. For example, for higher class I&C systems, then we want increased redundancy. So you might end up with 3 or 4 trains of system to provide that level of redundancy and reliability. So I mentioned equipment qualification. What is it? Well, it's verification that the equipment is capable of performing its safety functions through the life, the qualified life. So there'll be a specified lifetime it needs to achieve that over, and also in all environmental conditions that it can expect to see. So this is where we need to understand the fault conditions that may be present when we're expecting the equipment to operate. There are 2 main methods of demonstrating qualification. We can either do it by testing. So that's through, we could test the actual equipment itself and demonstrate it's capable of delivering its functions, or we can use type testing. So we can test similar equipment or claim qualification based on testing of similar equipment. There's also analysis. So we can undertake specific analysis and calculations to provide confidence that the equipment's capable, or we can extrapolate test data or operating experience of similar applications to again provide that confidence without actually testing the equipment itself. Or we can do a combination of testing and analysis. Again, it's not a one or the other thing. So the qualifications generally undertaken by the approved supplier. So approved suppliers will have been pre-qualified by the licensee. They'll have been identified that they've got suitable quality and arrangements in place on any required certifications that they need to provide the type of equipment that they're looking for. And they do the qualification generally because obviously they understand their equipment, they understand the plant best. But when there's specific sort of specialist capability that's required, then it's not credible to expect all suppliers and organizations to have that capability in-house. So qualification may also be undertaken by the licensee themselves if they have that capability, or by a third party. So things like electromagnetic compatibility testing, there are specific test houses that are authorized to do that, and seismic analysis. You might, if you need to demonstrate that your equipment remains functional in a seismic event, and you might send it off to get shaker table tested, or there might be some actual seismic modeling done. I mentioned already there's a defined qualified life for components, and that needs to take account of aging effects. So it's not just qualifying at the start and then that's it. We need to be able to confidently say that it will retain an adequate level of performance all the way through its qualified life. And that's where we want to build in qualification or design margin. That takes account of any potential uncertainties in the definition of the conditions, the environmental conditions that it needs to operate in, or the original requirements from the safety case, and also any variations in the production output. So there may be slight variations in the quality of items that come out of the production line. They may well be within tolerance, but it takes account of all of that. And ultimately, the evidence that comes out of the qualification process will be a whole host of records and documents. It could be things like test results where we've undertaken specific testing. It could be production QA, where there's quality checks undertaken during the production process to confirm that everything's okay. If we are relying on testing, we might need to see equipment calibration, test equipment calibration record to show that the test equipment was appropriately calibrated when the tests were undertaken, so that we can have confidence in the results. And there may be other things like storage. Maybe there's some specific environmental conditions that the equipment needs to be maintained in before it's delivered to site. We may need evidence of that, or materials traceability. If it's things like primary circuit components, or we might be claiming very high levels of integrity on them, we really need to understand where the materials come from, and that at all stages in the process it's got the correct chemical makeup and things. So we might need evidence of that. So the equipment qualification process itself is split into, in the IAA guidance, it splits into these sort of three main chunks. There's the design inputs. So that's really the design and safety process that I've talked about, where we identify what can go wrong. We define the safety functions and the conditions that the equipment needs to operate in, including in fault conditions. Then there's establishing the EQ, which is where we talk about this effectively through the procurement process. We specify the requirements that are driven from the safety case in the plant specifications that go out to the suppliers. And they're ultimately demonstrated through qualification with appropriate qualification evidence. And then there's preserving EQ. So we need to manage it through the life of the plant. The installation and maintenance requirements, we need to make sure that we every time we maintain the equipment, we aren't undermining any of the qualifications. So electrical cabinets, for example, we may be making claims on them being sealed against water ingress. We need to make sure that when we undertake maintenance, we reinstate that capability at the end so that we haven't undermined the safety case. And then things like condition monitoring to make sure that the plant continues to be within its in an operational condition. It's not degraded. There's no mechanisms that are affecting its performance. And also OPEX, if we monitor and record OPEX, and if we identify any issues from other plant due to OPEX, then we need to factor that in as well. So I'll quickly run through some quite naughty examples, just to give an idea of the sort of requirements that might appear in specifications that have originated in the safety case, and an idea of where they might have come from and why. So if we look at diesel generator, for example, Apologies about the picture. I'm sure most diesel generators in the nuclear industry are a bit shinier than this one, but it's the only one I could find. So the safety function, if we say the main safety function, is to provide a reliable source of backup power to essential consumers in the event of a loss in normal supply. So if we lose the grid, we've got all of our safety systems. We need to keep them powered. So that will be a safety function in the safety case, and that will drive a number of requirements on the diesel generator itself. So it's a very important function. It'll be a category A safety function. Effectively, the diesel generator will probably be a class 1 system, which will have a high reliability claim on it effectively. So we might have to do reliability assessment to underpin that. There'll be performance requirements. So there'll be a specified power, which needs to be delivered, which will be based on the worst case loadings from all of the essential systems in the worst case fault conditions. There'll be maybe design margin built in there as well to give us ability for future modification, or also in case there's errors in the calculations. So we want a bit of margin in there. There may be voltage and current requirements. The output will have to be of a specific quality. We'll need to demonstrate that. And also efficiency. So the safety case will be making claims on the ability of the plant to run for extended durations, and then potentially, adverse environmental conditions, very hot or very cold. We need to understand if that has an impact on the efficiency of the plant. And so we can be confident we still get the required power output and for the duration we need it. So for hazard qualification perspective, there may be things like IP ratings, so ingress protection. We might be worried about, if we've got fire systems in there, we might be worried about deluge. So we might want the systems to be capable of withstanding water dripping on top of them. Extreme ambient temperature I've already mentioned, and seismic qualification. I mean, there's no point in having a backup electrical supply if a seismic event can cause it to fail, because that's one of the main initiators for loss of grid. And then testing. So the safety case will also have claims on how quickly the power can be provided. So you might have to do run-up tests to demonstrate they can get to steady state running within a specified time. And duration testing, like I said, we'll be looking to provide power for extended durations. We may have to demonstrate that through testing as well. So if we look at some pipework and valves, it could be primary circuit pipework, and the safety function might be containment of primary coolant. So this will obviously have performance requirements driven by its normal operational function. So pressure, temperature. There might be specified valve closure times in fault scenarios. We need to ensure that the actuator and the valve can close within a specified period, because that might be assumed in the fault studies that have been undertaken. There'll be standards, specified standards. So I mentioned RCCM and ASME there. So that's a French and equivalent American standards for integrity, or ISO and EN standards for things like welding and things, and pressure system safety regulations. So all of these things might make their way into the specification from the safety case. Hazard qualification perspective, again, if it's primary circuit pipe work, we want it to be seismic qualified. We might have to do that. We might have to have seismic dampers or pipe hangers or things, so it could affect the design. So we need some analysis to back that up and demonstrate that it will maintain its integrity. And there may be elevated temperatures in certain fault conditions or pressures that the pipework may see that's above and beyond what we would expect it to see in normal operation. But again, if we're making high integrity claims on its containment function, then we need confidence that it's capable of withstanding those challenges. And there may be some more unusual things like material issues. So if it's primary circuit pipework, we're worried about activation of steels, so they need to be low cobalt. We need to avoid things like stellite on valve faces, which is used because it's hard wearing. And material traceability in manufacturing QA. I said before, if we're making very high integrity claims, then we really need to clearly understand where the materials come from, how it's been manufactured, and at each stage of the process have evidence to show that it is has got the correct makeup and will be capable of have the right strength and everything at the end. And then there may be specific assessments like pipe stress, for instance, is used to demonstrate the integrity of pipework. And finally, just quickly run through an instrumentation and control example. So again, very similar. If we look at the fault detection, trip and post-trip fault sequencing, there may be architecture requirements. So specific things that a specific architecture that we're looking to implement depending on the class of the system. If it's class 1, I mentioned before, it might have several layers of redundancy. We might need to build in testability functionality to be able to maintain and monitor the EQ through life. There may be there are lots of standards that might be specified dealing with lots of different aspects of I&C, like design, separation, classification of functions, depending on the class of the system. There are different requirements and different qualification requirements. With hazard qualification, again, we might need IP ratings like for humidity or dust ingress. We want to prevent things getting into the cabinets and affecting the performance of the equipment. Extreme ambient temperatures, again, seismic qualification, or radiation hardening. If we're looking at sensors, for example, flux sensors that are operating in the cold environment, then we need to demonstrate that those are capable of functioning in extended exposure to radiation. And there may be specific tools to enable us to do this. There's an emphasis analysis that looks at production excellence, all the QA throughout the production to provide confidence in the final system. Or FMEDAs and things, it might only be a specific failure mode that we're concerned about. Therefore, licensees may ask to see the full SIL assessment and failure modes and effects analysis, not because they want to start building these things themselves, but because they want to just understand the contribution a specific failure mode makes. Future developments, just the final slide. There's not an awful lot going on, but one thing that has been talked about a lot is harmonization. Every licensee does things slightly differently, which obviously means that you have to have specific qualification for each licensee, which has a knock-on impact for suppliers. So in the Nuclear Industry Council proposals for the nuclear deal, the government has subsequently published, recognized this need for a new equipment qualification centre and national method for qualification to try and avoid repeat qualification by having one method that allows companies to qualify products for the industry and potentially for international requirements at the same time to avoid duplication of effort. Oh, and there's some further information that you can have a look at your leisure. And that is me done, I think. So hopefully there's something useful there for some of you. And I'll try and answer any questions.
Okay, Stephen, thank you very much. Well, that was definitely a very clear, structured and informative presentation. So I personally learned a lot from that. Thank you very much indeed. Just to confirm to the audience that the slides and the recording of this webinar will be available on the NIA website afterwards. Well, it's not later this week. But if you have any problems accessing those slides, then please contact Stephanie McKenna and she'll provide them to you. So we've had a couple of questions in, Stephen, which I hope you're happy to field now.
Okay, I'll try my best.
Should be fine. So for a layman, for somebody who's not particularly technical, when's a safety case required? When do you need to have a safety case?
Well, I tried to cover it earlier briefly. It's when your plant or process involves handling sort of more than minimal quantities of specified radiological material, so radionuclides. So it covers things like reactor plant, obviously. Anywhere else that you've got significant materials, so waste facilities, fuel manufacture facilities, things like that, they will all fall under Nuclear Installations Act and required to be licensed by the regulator. Other activities, things like hospitals, where they handle sources, sealed sources and things that are small amounts of radioactive material, they don't require a site license, but they just come under the ionizing radiations regulations that I mentioned. So it just comes down to basically the quantity of material that you're handling and the potential hazard it poses.
Okay, thank you very much indeed. You also talked about, one of your sort of final slides was talking about future developments.
Mm-hmm.
And we've had a question in, which is talking about the way the industry is changing and the increased use of sort of digital instrumentation, etc. Do you think this is going to have much of an impact on sort of safety case methodology or any implications?
Well, nuclear industry is historically slow to respond to developments in technology, and I think it was seen for quite a long time as a challenge, the impact of smart instruments, because obviously there's obsolescence issues, meaning that licensees, existing operators, can't obtain the sort of dumb instrumentation and equipment that they had previously. And there are obviously concerns around when software gets involved, that there's potential unknown faults and things that could be in there. So I think there's been a lot of work done on that, and I think the industry has got a lot more accepting of I&C and software and things in particular. I mean, there are challenges. I worked on a project before where we were buying more of the same detector head. They had the same model number. On the outside was effectively the same piece of equipment, but the supplier had handily installed loads of a PLC with loads of additional functionality that they thought was really useful, but ultimately was a bit of a problem for the safety case, because it was now introduced a load more faults that could go wrong, and it wasn't something that was required. So, and that was discovered late in the process, because on the face of it, it was the same piece of equipment. So I think that's why it's really important that you need to manage configuration control of both in the supply chain and licensees to understand when changes are made, that we can just assess the implications of those and demonstrate they're okay. So I don't think that's a bit of a rambling answer, but if that's helped.
That's all right. Thanks very much. Another question: is there any consistency internationally in equipment qualification?
Well, I'm not au fait with the equipment qualification practices in the rest of the world, but I have had some involvement in GDA. So I mean, generally the industries, each country will look at the IAEA standards and guidance as a starting point, and that's their regulatory regime will be based around that. Other regulatory regimes tend to be a bit more prescriptive than ours, so you might find that the requirements are pre-specified as to what you need to do to demonstrate a Class 1 system, a Class 1 civil structure, for instance. But generally, the requirements are equivalent, and that's when working in GDA, we've done a bit of work there where it's rather than looking at requalifying things, you do look at equivalence of the standards that have been applied and the evidence that has been provided against what you would expect to see in the UK. So generally, the output of that has been that certainly between Japan and here, there was reasonably good consistency in what was considered to be a Class 1 and Class 2, 3 system, and the sort of evidence and qualification you would provide. So I think there is a level of consistency, but it's not always evident.
Okay, thank you. We've got a few more questions, actually. Can equipment qualification be inherited from previous generations, i.e. grandfather rights?
I think you can, and we talked about qualification. you can do testing or type testing, and you can also use analysis and OpEx from previous applications. So yeah, it is possible. And I think if you can demonstrate that there's no fundamental change in the functionality or the materials and things, that it's, you know, it's effectively the same product. It might just be a slightly enhanced, or modified version. That any changes aren't significant. Then yeah, I think you could claim inferred qualification. But you just need to be wary of, like, that case I mentioned where there was additional functionality and things have been introduced. In instances like that, then you would need to requalify, because there are, you know, it's no longer effectively the same component. It has additional functionality.
Okay, so what kind of events trigger would trigger having to review a safety case?
Having to review a safety case, well, there's lots of things. There's it could be international OpEx. I mean, there was lots of work done off the back of Fukushima worldwide. All regulators reviewed their safety cases in their plants against those events. It could be obsolescence issues. It could be, you know, degradation mechanisms where things are starting to no longer performing as reliably as they should be. Changes in standards or regulatory expectation, you might require you to review against, or if you identify potentially new faults, things that weren't foreseen before, or new hazards. So there's a whole host of things that could cause you to go back and revisit it.
Okay. Another question here. How do we ensure that risk models correctly reflect the real risks of the plant?
Oh, that's a tricky one.
I'm sorry, I didn't intend to be.
It's difficult, because it depends on how, you know, detailed your model is, whether it adequately reflects the plant configuration as is, and all of the potential failure modes and things, and a lot of the time getting your hands on decent data to put into it. You might not have failure rate data for the components if there's only a handful of them in existence. So yeah, it's very difficult, and I think you always have to treat it with caution. I think the one thing risk models are very good at is looking at the implications of changing. So you identify a baseline, and then you can assess the impacts of changes to that baseline. Okay. As far as convincing yourself the numbers are accurate, I don't have an answer to that one.
Okay, thorough answer there. It's actually a final question now, and it's quite a long one. Generally, how well are safety case requirements captured within plant item specifications, or not? Supporting through life management and avoiding divergence between the safety case and plant stroke components specification. So, for example, hazard qualification. We've got 1 minute to go. So
yeah, okay, I'll try and be quick. It's not an area that I have a vast amount of experience in, but my personal opinion is that things have got a lot better. Certainly with new build, there's a far better understanding of the need to manage the plant configuration and understand the qualification requirements and performance requirements, adequately capture those in procurement specifications and things, and manage them going forward. So I think it's a lot better than it was previously, because the importance of it wasn't really understood, and we learned it the hard way. But yeah, I'm sure there's still a lot of room for improvement, and a lot of the new tools and electronic software tools available might help us do that.
Okay, fantastic. I'm going to have to wrap it up there. So I'm just going to say, listen, thanks ever so much. It was very interesting. Thank you for the presentation. Thank you to everybody who signed in today, and particularly those who posted questions. Thank you. And I will say a final thing about the CRA forum that you mentioned earlier. I went a couple of times and it's very good. So the audience, maybe keep your eyes open for when that happens this year. Thank you very much and have a great afternoon. Thank you. Cheers.
Thank you.
Bye-bye.
Bye.